So, good morning to everyone, and today we are going to continue from where we have left in the yesterday's class. So, yesterday we have seen about the inverters. We have just started the inverters and we have seen the introduction of the inverters. So, basically, we have seen that how an inverter will look like, and then what are the various voltages in the inverter VTC. Okay, because this VTC which we have plotted is the DC characteristics. Okay, is the DC characteristics of the inverter. So when we see the DC characteristics, then what are the important like voltages like VIL, VIH, VOL, VOH and VTH. So these are the 5 important voltages which we have seen yesterday, the definition of these voltages, and we have also seen how an ideal inverter will look like and how the VTC of an ideal inverter will look like. And when we see the practical case, not the ideal one, then how the VTC changes. Okay, and this is VTC will be different for different inverters. So this is what we have discussed yesterday. So now today we will continue from there only, and we'll see that how to derive this all voltages, the formulas for all these voltages. And in fact you can sometimes directly use the formulas, or you can start as per the requirement of the problem or your design issues. You can start from the very basic equations as well. So today we are going to see this all up to the all the 5 voltage of all the 5 type of voltages which are seen on the DC characteristics. We are going to see all of them, how to get them. But before that, we will see that how to get the voltage transfer characteristics, because up till now we have seen a driver and we have seen the VDC in general form. Okay, we have not seen how to get the VDC basically. But the VDC which we get, which we'll try to get here, is actually derived or actually like obtained from the basic fundamentals. So these fundamentals are related to your load line analysis. So whenever you have, let's say, a transistor and some resistance connected to it, and you want to determine the quiescent point, the operating point of this transistor, that at a particular voltage, at at any applied voltage, where will be the quiescent point of this circuit, okay, or where will be the stable point, or at which point it will be biased. So that biasing voltage will be determined by the load line analysis. So what we do, we basically plot the characteristics of the transistor, and then over to that we plot the this resistance line, and then we see that where they intersect with each other. So that intersection point is basically your quiescent point, and when you apply some input, so that input is like varies across that point, that quiescent point. So the same concept we are going to apply here as well to determine our operating points for a CMOS inverter. So you see, if you start with, so you have a CMOS inverter looks like something like this. So the same circuit which we have seen yesterday. In case of DC circuits, although we don't show the capacitance will be more useful when we will do the dynamic analysis, okay, the transient analysis, which we'll do in the next chapter. Okay, if once we'll complete the DC characteristics, then we will move on to the AC characteristics or the switching characteristics. At that time this capacitance will be more important. But still, if you see the circuit in the general form, then the circuit will look something like this. Okay, so at the connections of the gate we apply the input, okay, and at the connections of the drain of the 2 MOSFETs we apply a capacitor, okay, and that is the total load capacitor. This load capacitor is actually consists of intrinsic as well as the extrinsic capacitors. Extrinsic means the capacitor which is because of the this parasitic wires and all these things. Whereas the intrinsic capacitance is because of the capacitance of various this MOSFETs itself. So this is what it is, and the interconnect wires and all those things. So that will come into the extrinsic capacitor. So let's start with. So basically, if you want to determine the this voltage transfer characteristics, so we have to start with the characteristics of NMOS as well as the PMOS. So we know very well the characteristics of an NMOS, but we don't know the characteristics of a PMOS. So we'll first see the characteristics of NMOS. We have already seen in our previous classes, so we will not see those characteristics. But if in general I want to tell you, so those characteristics will lie in the first quadrant, okay, whereas the characteristics for a PMOS will lie in the fourth quadrant, will lie in the third quadrant. The characteristics of NMOS will lie in the first quadrant, whereas the characteristics of PMOS will lie in the third quadrant, right? But this third quadrant is basically what we do. We plot the V out, okay, this V out with respect to your ID, so drain current with respect to V out. So this is our output characteristics. So what we do is, you see, one of our transistor NMOS is working as a driver, whereas the upper transistor PMOS works as a load, okay, in one situation. Whereas in the other situation, okay, when your input is low, in that case PMOS becomes the driver, whereas the NMOS becomes the load. And if your input is high, then in that case the opposite, which I have told earlier. So NMOS becomes the driver when the input is high, and PMOS becomes the load. Okay, so let's say if we just assume the NMOS is the driver and PMOS is the load, then our NMOS will lie in the first quadrant. And if you want to get the intersection of the PMOS characteristics with the NMOS characteristics, then we will like to plot the PMOS characteristics, which are initially in the third quadrant, into the first quadrant. So to do that, what we do is we shift that, okay, we shift the characteristics. So to shift the characteristics, you can see in this lower leftmost diagram, that if we plot the IDP versus VDSP for different values of VGSP. So as you know that the threshold voltage of a PMOS is negative. So the gate to source voltage, the PMOS will operate for negative voltage of VGSP. So as we keep on increasing the gate to source voltage, then our drain current in a negative direction will increase. So this is what the first diagram reveals, okay. But then what happens is, if we want to shift this characteristics in the second quadrant, so what we have to do is we can use these general equations. So you see, what are your general equations? Vin is equal to VDD plus VGSP, okay, for a PMOS. And as you know that IDN is equal to minus of IDP. So if this is in the first diagram we have plotted your IDP, then now we want to see that IDN will be on the positive x-axis. IDP is obviously we have plotted in the positive x-axis, but it will show in the negative side. So you see, if you want to do this, so our VGSP will become how much? So you see, these equations which we have, this equation which you can see here is Vin is equal to VDD plus VGSP, and IDN is equal to minus IDP. So these equations are basically the equations which we have seen yesterday, okay. So these equations are the equations for your PMOS. So as you know that your PMOS will operate in the saturation region if your input voltage is less than VDD plus VTP, okay, and simultaneously VDSP is less than VGSP minus VTP. Okay, and if you substitute the V in and V out instead of VGSP and VDSP, as we have seen yesterday in yesterday's class, then you can rewrite the equation, the same equation which is written in terms of VDSP and VGSP over here, then you can use directly these equations. So Vin is equal to VDD plus VGSP and IDN is equal to minus IDP, and Vout is equal to VDD plus VDSP. So these are the equations which we have seen yesterday. So now as we want to what? This transfer the characteristics from the third quadrant to the second quadrant. So then what we have to do is, you see, you have to substitute this various values in this equation. So let's say if you substitute Vin is equal to 0 in the equation, okay, or if you substitute, I mean take the leftmost diagram, and if you substitute VGSP is equal to minus 2.5 in this particular equation, so your Vin will become equal to how much? If you consider VDD to be equal to 2.5, then VDD is equal to 2.5 and VGSP from this previous characteristics, you can see that for VGSP is equal to minus 2.5, if you substitute it here, then your Vin will be equal to 0. Okay, so for Vin equal to 0, and if you consider that IDN is equal to minus of IDP, then previously I have plotted minus of IDP. Now you can plot it in the positive direction. Okay, so IDN, if you want to plot it in terms of positive, so you can write it as IDN, positive side. And so your Vin, whatever you got the characteristics for VGSP is equal to minus 2.5, the same characteristics you can show it for Vin is equal to 0. So this characteristics for Vin is equal to 0, which you can see here, is the upper one, which you can see here, is your this one for Vin is equal to 0, whereas the lower one is for your VGSP is equal to minus 1. So in the same equation which we have seen, this equation, okay, this equation particularly, if you see, so Vin is equal to VDD plus VGSP. Now if you substitute VGSP is equal to minus 1, then, and VDD is equal to obviously 2.5, then you can see that Vin will become equal to 1.5. So for Vin is equal to 1.5, your PMOS characteristics will be the lower one. Okay, so you see, this is how you get this particular diagram. Now the other thing is, you have to now shift it from second quadrant to the first quadrant. To do this, we have to again use you have to make use of this equation. Which equation? This particularly Vout is equal to VDD plus VDSP. Now VDSP is substituting the different values of VDSP. Let's say if you substitute VDSP is equal to 0, then if VDSP is equal to 0, okay, then Vout will be equal to VDD. So you see, this is what you can see here. So your Vout will become equal to VDD. Now if your VDSP is equal to drain to source, okay, so in case of PMOS, source is the most positive one. So if your drain is at lower voltage, then what will happen? Vout will be less values, and when your VD reaches the maximum value, so in that case, if VDSP is maximum negative, so VDD minus VDSP, because VDSP maximum can reach up to VDD, so VDSP maximum can be equal to minus of VDD. So in that case, VDD minus VDD, so Vout will become 0. So you can see this particular thing in the this last diagram. So if we plot this particular values in the these values, so then we will get the curve in the first quadrant. So this is what the method, how to get the characteristics from third quadrant to the first quadrant. Okay, now once you have plotted these characteristics in the first quadrant, now what you have is, the characteristics of the NMOS are there in the first quadrant. Okay, you have plotted already them in the first quadrant. So assuming them in the first quadrant, and if you now shifted the PMOS characteristics also into the first quadrant, and now if you plot them simultaneously, the characteristics will look something like this. Okay, and from this characteristics you can see that how you will get your CMOS VTC. So to get the CMOS VTC will be the next step, but what we do is basically we have plotted. These are the NMOS characteristics which you can see by the arrow, okay, and the other characteristics which we have seen in the last slide, you have plotted over the NMOS characteristics. Now you can see that the NMOS characteristics are intersecting with the PMOS characteristics. So PMOS characteristics are basically the load characteristics, okay, the characteristics of the load, okay, load resistance, or you can see the load MOSFET, whereas the NMOS characteristics is the characteristics of the driver MOSFET. Now you can see the intersection, the point of intersection of these two characteristics. Now for various values of input voltages, you can see that let's say if you take input as Vin is equal to 0, so for Vin is equal to 0, the NMOS characteristics will be the lowest one, okay, near the x-axis. So you can see that the NMOS characteristics for Vin is equal to 0 will be this one, okay, whereas for PMOS the characteristics for the PMOS for Vin is equal to 0, as you have seen in the previous slide, that will be the highest one. So for Vin is equal to 0, the characteristics will be this. So for these two characteristics, the point of intersection will be this particular one, okay. So this point is the point of intersection of the NMOS and the PMOS characteristics for Vin is equal to 0, okay. So you have to just see that first. Now as you keep on increasing the Vin, then the characteristics also shifts. So as the characteristics shifts, the point of intersection also changes, okay. So you see, when you make Vin is equal to, let's say, 0.5, so for 0.5 the NMOS characteristics will be this one, okay, whereas the PMOS characteristics for Vin is equal to 0.5 is this one, okay. Now the point of intersection of this two will be this one. So this is the point of intersection of these two characteristics, okay. Now for Vin is equal to, let's say you consider Vin is equal to 1.5. So for 1.5, as you can see that the NMOS characteristics will go up. So this characteristics. So this is the Vin characteristics for sorry, not this one, but basically this characteristics, okay. So you see this characteristics which is going towards the right side is for Vin is equal to plus 1.5 for NMOS, whereas for PMOS the characteristics will be this one, okay. So Vin is equal to 1.5. So when you intersect them, the point of intersection for Vin is equal to 1.5 will be this particular point, okay. So you can see the various points here. Now similarly you can plot the various intersection points for other voltages, let's say 2 and 2.5. Now if you plot this intersection points separately, then okay, what you will get is, from this characteristics you can easily understand that when your Vin is equal to 0 or when your Vin is equal to 1, okay, in that case you can see that in which region, or for different points, as you have seen, in which particular regions your NMOS and PMOS are working. So you see, for Vin is equal to 0, as this is the point of intersection, at this particular point you can see that the NMOS is in cutoff, okay, whereas your PMOS is in linear region, okay. So you see, that is what the important thing is. But if you make Vin is equal to 0.5 for this particular point, then at this point your NMOS, see, the NMOS is lying in this point is lying on the NMOS characteristics in the saturation region, whereas for the PMOS it is lying in the linear region, okay. So this is how you can from this graph itself you can see that at various points, at various input voltages, as the input voltage changes, how the point of operation of the two MOSFETs changes, okay. So to further elaborate it, you can see that for Vin is equal to, let's say, 1.5. So for this you can see that the NMOS is working now in the linear region, whereas the PMOS is working PMOS is working in the saturation region, okay. So this is what you can see directly. So as your input voltage changes, the point of operation of the two MOSFETs also changes. Sometimes NMOS works in the linear region, whereas PMOS works in the saturation region or the cutoff region, or whatever the situation is, depending upon the input voltage. Okay, so this is what the important thing is. Now, if we plot this intersection points together on one curve, okay, like this, and if we say, you see, now what we are trying to do is we are trying to plot the input voltages which we have seen here, okay, V is equal to 0, 1.5, 1, 1.5, 2, 2.5. So this will become our input voltage. Now if we try to plot this input voltage with respect to your output voltage, so output voltage is your the voltage which you have taken here on the y-axis, on the x-axis. So this will be your output voltage, whereas the voltages which you can see here increasing, written over the characteristics onto the characteristics, that voltage will become the input voltage. Okay, so if you plot this voltages together on a single curve and you call it as the plot between V in on the x-axis and V out on the y-axis. So this plot is basically your voltage transfer characteristics. Okay, and to get this voltage transfer characteristics, what we have done is those point of intersection which we have seen in the last slide, we have plotted all this point of intersections together, okay, on this curve, and then we have joined them. So after joining them, what we get is what is called as your voltage transfer characteristics, and from this you can see that your NMOS and PMOS operates in different region. So for a few of the points I have told you that in which region they operate. So those regions of operation you can see very clearly in this particular slide. Okay, so NMOS, as I have told you earlier, that NMOS works in the cutoff region, whereas PMOS works in the resistive region. Okay, then similarly you can find for the other intersection points. So in the previous slide you can see there are 6 intersection points. So in this slide also you can see that the 6 points we have made, and for this 6 points you can separately point out that in which regions the MOSFET will work. Okay, so you see, now if you see these characteristics and if you try to understand, okay, basically this in detail, so we can see that your CMOS, okay, CMOS characteristics, this you can see, this is not difficult to understand, but this characteristics is very important to understand or derive the various voltage equations. Okay, the equation for VIL, VIH, VTH, okay, VOH, VOL. So this particularly things if you want to determine, it is necessary to understand the CMOS VTC very clearly, and not only the CMOS VTC but its various regions. So in various regions, in which region, okay, if you consider, let's say, this whole VTC, CMOS VTC, then you can separate the CMOS VTC into 5 regions, and in these 5 regions the operation of the NMOS and PMOS is different. Okay, so the NMOS and PMOS operates in different regions. Okay, so in let's say region A, if you consider the part A of this curve, so this particular region if you consider, then you can see that in this region basically what is happening, your from this table you can see very easily, this table is the same. We have drawn this table from our previous explanation. So in this region you can see that what is happening. So I'll try to explain you these things. Okay, so what is happening in this particular region A, your input is low, so input is on the x-axis, okay, and output is on the y-axis. So if input is low and as it is working as an inverter, so your output will be high. Okay, so if your input is low and output is high, so in that case we are basically, what is happening, with our PMOS is working and NMOS is cut off. Okay, so you can see here, and your output will be near to your maximum value. So it is, the maximum value is VOH. Okay, so you see this region A. So in this region A, how will differentiate this region A? How will demarcate this region A? So this region A is demarcated basically from 0 to VTN. Why VTN? Because you see, in this region your NMOS is in cutoff. Okay, so NMOS will remain in cutoff till the time your gate voltage is below VTN, is less than the threshold voltage of the NMOS. Up till that time only the NMOS can be in the cutoff region. Okay, so basically this region A, your NMOS is in the cutoff region, whereas the PMOS works in the linear region. Okay, why it works in the linear region? Because it satisfies your linear region condition. So this is the condition which we have seen in the last class. Okay, so you see, now in region B what happens is, you see, in region B, as you can see, that the region B is demarcated as from VTN to some point. So that some point is what? You see, now your this NMOS will come into the saturation region directly. Why it will come into the saturation region? Because it satisfies your condition, this one, and for this particular value, which is this line which you can see here, up till this line which you can see here, this particular line, above this line your NMOS will work into the linear region. Okay, sorry, it will work in the saturation region. Why it will work in the saturation region? Because here your Vout, that is your VDS, is equal to Vn minus or VGSN minus VTN. Below this line, this Vout will be less than, Vout is this on the y-axis. So you see it is decreasing. So Vout will be in this particular line, below this line, VTN, this Vout will be less than Vin minus VTN. Whereas above this line, the Vout will be greater than Vin minus VTN. At this particular line, Vout will be equal to Vin minus VTN. So as you know that if your VDS is greater than VGS minus VTN, and obviously VGS is greater than VTN, then in that case the device walks into the saturation region. So you see the horizontal line which you can see here in this particular triangle. Okay, so this horizontally marked triangle, in this particular region your NMOS works into the saturation region. Okay, so this is very clear to you. Now you see, because of this what happens, and similarly you can differentiate the thing for PMOS. So in this case what happens for PMOS, in the PMOS, for the case of PMOS, what happens, your this particular line, which line? This one, sorry, for this line, if you consider this line, then for this line basically what happens, below this line your PMOS works into the saturation region, whereas above this line it works into the linear region. Okay, so this is what the difference is, and the reason is same which we have seen for NMOS, exactly opposite if you will do, it will become for the PMOS. Okay, so the things will be exactly same. So below this line, then the PMOS will work into the saturation. Above this line, it will work into the linear region. Okay, so you see what will happen now. If you see in the region B, what will happen, your NMOS will work into the saturation region, whereas your PMOS will work into the linear region. Okay, whereas in the region A, it was NMOS is in the cutoff and PMOS was in the linear region. This we have already seen in our this characteristics, where we have seen the intersection of the two curves. Okay, now if we consider the region between the two these lines which we have seen earlier, then region C basically. So in region C, both of our transistors, NMOS as well as PMOS, works into the saturation region. So this is the region in which both of the transistors works in the saturation region. Okay, now if we move on to the region D, then in the region D what happens, as per the previous discussion, NMOS will come into the this linear region, because the point is this particular region is below this line, which is Vout is equal to Vin minus VTN. So below this line the transistor will be into the linear region. So in the region D, the transistor, the NMOS works into the linear region, whereas the PMOS start working in the saturation region. Okay, whereas in the region E, what happens in region E, your NMOS still works in the linear region, whereas PMOS works into the cutoff region. Okay, so this is what happens, because now you see this PMOS is completely cut off and the capacitor is discharging. Okay, yeah, it is discharging through the NMOS. So NMOS is working, PMOS is not at all working. So PMOS is in the cutoff. So you see, this is very important to demarcate these various regions on the characteristics on the VTC. Why this is important? Because you see, now if you see this this various voltages which we have defined yesterday, the voltages like VIL, which is this VIL will fall into the region. If you see it clearly, I mean, if you can try, if you see it, then you will find that this VIL will fall into the region B. Okay, and in the region B, what happens? Your NMOS works into the saturation region, whereas your PMOS works into the linear region. Okay, so if whenever we will derive the equation for VIL, we will consider the NMOS to operate into the saturation region, whereas the PMOS to be operated in the linear region. Okay, whereas if you want to derive the equation for VIH will fall into the region D. Okay, so in this region D, what happens? Exactly opposite. So NMOS will work in the linear region, whereas the PMOS will work into the saturation region. Okay, so this is important, and this is important because you see in the previous slide which we have seen that IDN is always equal to minus IDP, because in the DC, because when we do the DC analysis, no current goes into the output and the input. Okay, because whatever current comes from the load goes into the driver. Okay, as there is DC circuit and there are capacitances in the input and output, so no current will go into the input and output, so all the current will remain into the circuit itself. So that is why IDN is equal to minus IDP. Okay, so you see, because of this, we have to take the drain current equations of NMOS as well as the PMOS. So which equation we will select? Whether we will select the linear region equation or the saturation region equation. So that will depend upon in which region it is operating. Okay, and as we have seen that for different regions the equations are different, and you have seen that VIL falls into the different region, so you have to use different NMOS equation and PMOS equation, not the same one. Okay, you can't use the saturation equation for both NMOS and PMOS while deriving the equation for VIL, and similarly for VIH. Okay, so you have to use different equations depending upon the region in which it operates. Okay, now similarly, if you want to determine the threshold voltage of the inverter, not the threshold voltage of the NMOS, not the threshold voltage of the PMOS, because they are like constant, but if you choose some NMOS and PMOS and combine them to form an inverter, then there will be some threshold voltage of the inverter as well. So that threshold voltage of the inverter will lie in region, basically you see, ideally it should be what? Ideally noise margin should be equal into the upper side as well as in the lower side. So for the ideal case, your VTH should be equal to VDD by 2. So if it is VDD by 2, then your VTH should lie in the region C. Okay, rather than any other region, it should lie in the region C. So in the region C, both of the transistors will work into the saturation region. Okay, so when we will try to determine the threshold voltage of the inverter, we will take those equations accordingly. Okay, so this is why these regions are very important, and if you remember this particularly graph and this table, it will be very helpful for you to derive the things. If it is required, you can refer these things while deriving the equations. So you see, particularly we'll stop this today's lecture here itself, and we'll start from the derivation for VIL and VIH in the next class. Okay, so I'll stop my today's class here itself, and thank you to all of you for listening. Thank you.